Okay, let's get started. So here's the basic layout of what we're going to be doing, and it looks almost exactly the same as what we did last time, but instead of using this as a generator, we're going to use it as a motor. And instead of this providing power to force it to rotate, we're going to actually use this as a dynamometer, which is a torque device or a brake. It might be, because we were having some issues with that, we might actually try to use, let's see, there is this prime mover dynamometer. We'll see, we'll try it again, and because we had some problems with this on Monday's lab, but perhaps we'll try this unit to see if we get any different results. And we do actually have one of these units in the lab. We don't have one of these are quite expensive. But okay, so here's our basic setup. Let's go ahead and power up our DAC. So that's down over here. You can certainly use the one that's over here if you want. I just feel like this one, I don't know, it's always there. So I just run my wire over to it and then it's always on. So now my DAC is powered up. And now I'm going to go ahead and start connecting. So I'm going to provide power to my dynamometer. But if you click it on over here, I'm curious if this is operating, if we even need to provide power to this, because this is acting as a brake, we might not even need to have power. So we'll try it without connecting this with a power supply and then see what happens. The way that these dynamometers work, they use like an eddy current design, so it generates some heat. We'll see if this actually works. If it doesn't work, then we'll scrap it and we'll try a different one. But let's go ahead and connect our torque analog here. Oops. And then we'll connect our speed over to this terminal. And we'll connect our analog common to the DAC common. Oops. Can't seem to catch it right. Okay. So that's the first part of it. Now we scroll down to figure 4. So we're basically going to try to develop the V curves, which is shown in figure 3. And we're going to go ahead and try to develop figure 4. So figure 4 is developed if you only had a 3-channel DAC. We actually have a 4-channel DAC. So we're going to monitor the individual phase voltages going to the motor and the individual phase currents. So we're going to go ahead and connect these, and I'll try to make them so that they're fairly uniform looking. Here are our voltages. This is connected as a Y. We'll jumper that way and jumper that way. And now we're going to go ahead and monitor each of these individual voltages. So I've got one here. This voltage here, which is our phase B. And then lastly, here's phase C here. And then since we're monitoring the neutral point, let's just go ahead and grab one of these neutrals over here, and then we can jumper across like that. Okay, so now we have the 3-phase power that we can measure going into the machine. The next thing we're going to do is go ahead and get the field current, which the field current is going to go in here, and it's going to be a DC current. So we're going to run that into our I4. Our I4 is going to run over to one of these resistive load banks because we're going to put 200 ohms of resistance. So the 600 in parallel with the 300 is 200 ohms. We run that into our device, and then we run that back over to our neutral, and that hopefully is connected well enough so that we can get this to operate. Okay, so now we're going to go ahead and we're going to set this up to be a constant torque brake. We're going to do torque control, where we're going to set that to its maximum. And when we're ready, we'll start it. And then we're going to go ahead and we're going to turn this thing all the way up. And we're going to flip the switch. But before we do that, we need to read what the step says. So that's basically, we did step 4. Now we're going to go ahead and set up our metering and then our configuration. So we're going to turn on our metering. And we've got our 3 voltages here. This one's not being used. We have our three currents here. Our fourth current is the DC field, so we'll change that to DC. Then we're going to turn on our power. And this is the individual phase. This is just the voltage of the power for phase one. We're going to do the combination power. That's the real power. We'll do the combination power. But we'll call it Q. And then we'll turn that one on. And then we'll turn on our speed and our torque. So that's the first part. The torque, though, has to be this corrected value. So let's switch that to corrected. And there's some discussion about how to set that on in the torque corrected mode. All right. So we're going to set this into the closed position. So we're about halfway through paragraph number 5. On the synchronous motor generator set the exciter switch to the closed position and turn the exciter knob fully clockwise. So turn that fully clockwise. Turn the power supply on and set the voltage control knob to the value set it's about nominal voltage, which means this is fully on. We're going to go ahead and I'll minimize that a little bit. And so this is going to be in continuous refresh, hopefully. And then hopefully this is going to work. If this doesn't work, well, like I said, we'll have to provide power. So I'll pause here for a moment to give everybody a chance to see if they have any questions on the setup here, or are you still getting your circuit set up?
I just have a question on the 4-quadrant power supply.
Yeah.
I missed it. So you're setting it up as a constant torque brake, and then where where's the brake control?
The actual torque you apply?
Yes.
You can put a 3 in here, or you can just rotate this in the max direction until you hit 3.
Okay. Then
And then you get to make sure it's, yep. The power's on, so hopefully this works. I don't know. We might have to actually run the power supply to it. We'll check that in a minute. If it doesn't work, we'll just change that. So this is just a tweak because we weren't able to get this to work on Monday. Okay. Everybody ready to flip the switch, or do you still need a few minutes?
I believe I'm ready.
Brayden, are you ready?
Yeah.
Okay, let's flip the switch. And you can see here, there's no torque, there's no current. So what that tells me is this needs to be powered up. So let's actually run power here to here and here to here. So it looks like you have to have power supply going to it, even if it's acting as a brake. All right, let me try that again. And it's still not spinning. Why is it not spinning? Oh, sorry about that, folks. I made a mistake. I forgot to run the current through here. That was a big mistake. So you can see I ran it to the meter here. I actually needed to run it into my multimeter. So I kind of jump ship a little bit. So these go here and here. And this one is here and here. All right, now if we flip the switch, do we get current flow? We get a current flow, but the speed is still, it's still not spinning. So now, let's see if we can adjust this and see if we can start to get some speed. So I'm going to start to minimize this. Huh. Doesn't seem to be working. Let's try this one and see if that gets it to spin. So now it spins. there may be a problem with the software because before. This was not. So I'm still not getting any torque. Why am I not getting any torque?
I didn't connect them. That might be.
Oh, boy, thank you. You are absolutely right. I'm not connecting them. My thinking power is not there today, clearly. So, whoop, that's what I wanted to do. I'm going to put that module back in. Okay, let me put that back in since I hit the wrong button. And the only thing I needed to do here was run that, and that. Now I'm going to try it again without the power connected. But first, let's lower the front panel. Lower the front panel. I'm going to stop this. I want it to stop. Power's off. This is the hitch in the get along because I know, stop. Let me go raise the panel and see if I can stop it this way. Usually you can stop it from rotating. No, I can't rotate the panel. I can't stop it. I'm spinning.
See that I was able to just right click it and have it, it said to stop motor. It looks like it doesn't, like it's not letting you.
Yeah, I don't know why. I'm right clicking away and it won't allow me to stop. Well, let's just delete this module. That'll force it. Stop spinning because I've deleted it. So let's go ahead and put that back in. Lower the front panel. Like I said, I don't know what magic gets the wire to connect. There doesn't seem to be any rhyme or reason as to get these connected. Let me get you some help on it today. I don't know. Is there a trick? Are you guys able to get yours to work? You can connect the belt because you can see I'm trying to connect it. When it converts to a finger, you should be able to connect it.
Yeah, I was able to connect mine.
For some reason mine doesn't want to connect. Let me try to raise the front panel. Lower the front panel. I don't know. I'm gonna just kill it and start over again. Sorry about that. It won't take too long to get it set up again, hopefully. The security device is plugged in. Huh. Let me try that again. Not sure why I didn't register. Clearly, this is a glitchy software. So, all right, let me try that again. So, here's that. Here's my power supply. Here's my DAC, my resistor. All right. Now I got to go ahead and kick it up. I'll try to be somewhat efficient with my connections. Torque, speed, analog common, power. Now I run this to here, and here, and also run my currents here and here. This one to this one. And lastly, I'm missing a Y. And then connect this to neutral. This connects to here. That connects to there. Now I need my DC. So I'm going to run that to channel 4. Over to my resistor. Over here, and then back to neutral here. Okay. Now, let me turn this off again. Let's try connecting these. I don't know why this doesn't want to connect. Oh. I have no clue. I don't understand why I cannot connect my wires yet. All right, well, that's not working. So let me do it the same way you're doing it, which is through the software. And let's go to, I'm going to do it through the software, the same way you're running it. Shouldn't make a difference. We'll access the software this way. Okay. Go to my access code. Whoops. Did it just overwrite right space? Code. All right, let's see if this is any better. Next time, I'm actually going to put it so that I'm not going to connect any wires until I actually. Seems like the software online maybe is a little more effective because it has those features that were not available to me. So, okay. Now my resistor module. All right, power over. Okay. All right. You can tell the software's a little more updated because you can see that it highlights when it's ready to when you could actually accept a terminal. It's not able to do the wiring connections. Okay. All right, so I have that. Now I've got to run a voltage reference back over here and connect this one to this. So this one. Now, the last thing I need to do is run the DC. This resistor. Okay, I think, oops, forgot to do these connections here. Sorry about that. Okay, I think we're good to go there. We'll let's see. We'll turn this on. We'll set this to 3. We'll start it. We'll ramp this up. And before we turn it on, we'll set up our metering again. So we have E1, E2, E3. That's off. These 3 are correct. This is in DC. We'll turn on our torque. We'll turn that to corrected, and we'll turn on our value here. And then let's see if in this switch, so now we're going to go ahead and check our first case. So it says, set the exciter switch to the closed position. Turn the, and turn the exciter knob fully clockwise. Turn the power supply on and set the voltage control knob. Record the starting torque. So let us, I'm going to pull this out so I don't keep fumbling around with it. Okay, so now we'll do the continuous refresh. We'll flip the switch. And there's no speed. So that doesn't seem to be effective. That started. Okay, so we have a current flow. We have DC current here, but we have no RPM. So let's flip that switch off. And let's go ahead now and put power and see if this changes anything. If this doesn't change anything, we're going to skip this step. So turn it on. Still nothing. So it doesn't appear that with the switch in the closed position, it actually functions as intended. When we flip it over here, we do get a speed. So we're going to go ahead and skip step 5. And this is step 6. We can't do step 5. It doesn't seem to be working effectively. We'll go ahead and do step 6. So the torque that you're going to specify is the 2.73 Newton meters. Okay, so you can skip the comparison part. You don't have to worry about any of the details. Just for whatever reason, it doesn't seem to be working. And we're going to go ahead and proceed from there. Okay. So we are on to step 7. So let's go ahead and decrease this knob to minimum. So we'll bring it all the way down. And then we'll see that the speed starts to increase. And the speed starts to increase is because the machine is able to overcome the value. So we're going to set it all the way to minimum, which is essentially means it's 0. And that's the speed that it stabilizes at. 1748. Okay. So now this is where we have to think a little bit about it. And this will make more sense when we start getting into induction machines. But essentially with this field open, it's getting its excitation or its magnetic field on this rotating part. It's getting it from an induced value, an induced current that is being here. So when we talked about starting an AC motor or an AC generator or motor, it doesn't matter. We get an induced field. Excuse me. We're getting an AC from we need a rotating field that exists around here. We also need one here. And the only way you're going to get that, and we'll learn how this makes more sense, is if you have a difference in speed between synchronous speed, which is 60 hertz, or 1800 RPM when you're talking about a 4-pole machine, and the actual speed of rotation. That's why it's 1748. When I flip this switch, now you're getting a magnetic field that is DC and then it's locked on at this particular value. So you see when I flip the switch, that speed should go to 1800 RPM. So flip the switch and we instantly or almost instantaneously go to 1800 RPM. And that's again because you need an induced magnetic field over here on the rotating part. And the only way that you get an induced magnetic field if there's this difference in speed between rotational speed and synchronous speed. Okay, so for step 7, the answer is yes. The speed goes to 1800 RPM, and we did notice a speed change there. Now let's go ahead and vary this value here, this field current. And you'll see that my current here is changing, but let's look at my speed. My speed doesn't change at all, right? You can see that the speed has in no way, shape, or form changed. So for a synchronous machine, varying the field current, unless it gets to very low values, is not going to affect the speed. So the answer for number 8 is no, there's no change in the speed. But does the current magnitude vary? Yes, it does. Look, it goes all the way from almost 0.7. These are our field current values, or not field current, these are armature current values, all the way down to 500 milliamps. And we'll see why that when we start looking at section 9 and on from there. All right, so questions on that?
Nope.
Okay. So to do this part, we're going to go ahead. We're going to turn this on and we're going to get the 3-phase power here. This one is going to be 3-phase power. This is going to be Q. All right. So we have those values. Now we're going to vary our field current in this range here. And we're going to vary this field current value from 100 milliamps up to 800 milliamps. Okay. So we're going to have to use a combination of things, and we're going to use the data table capability to do the recording. So what I'm going to do is I'm going to measure the voltages, and I'm just going to pick one. I don't have to have, you can see they're all the same magnitude or approximately the same magnitude. So I'm going to go ahead and measure E1. I'm going to measure I1. I don't need the torque. I don't need the speed. I'm going to measure real power, reactive power, and I also want to measure the field current as well. So these are the boxes that you should check to go ahead and have your results displayed. Okay, so we click apply, and we have the data that we need to capture here. So I'll give you a second to go ahead and do that. Now I'm going to bring up Excel so we can do over here. Everybody all set? Everybody have all the stuff that they want to record?
Yep.
Okay, perfect. So now I'm going to start my recording, and I'm going to take this all the way down to 100 milliamps. So I'm going to adjust this min. That's not going to get me from there. So what I'm going to start doing is flipping on some switches to see if I can get to 100 milliamps. Would you say 98 milliamps is close enough to 100 milliamps?
Yeah.
Yeah, I would say that's close. Oops, I would say that's close enough for me. So I'm going to record that one. So this is our driving value, I4. Now I'm going to see if I can take this to 200 milliamps just by changing this field. Can't get there from here. So let's go ahead and turn on the 600, and I overshot it. So let's bring it back down. Would you say 208 is close enough to 200?
Yeah,
yeah,
Close enough for me too. Flip that switch. Now I'm gonna put these three on. Would you say that 307 is close enough to 300?
yeah,
All right, now let's see if we can get to 400 by flipping these on. Oops, I overshot it. That's pretty good, right? 402. Hit record. Now I'm going to go ahead and get to 500. And the only way that I can get to 500 is when I pull this one and I take these resistors completely out. So I'm going to just dump it over here. Bypasses that completely. And I'm going to bring this back down so that I get to 500. 504 is pretty close for me. Record. Go up to 600. Oops. 607 is close enough for me. Hit record. And you don't have to mimic the numbers I'm getting. I'm just doing it fairly quickly. 700, close enough. And then I think I crank this all the way up, and this is the maximum. Or here's 800. I need to go to 800. I shot it. Okay, perfect. Wow, that's lucky. I'm going to just do 900, even though that's really pushing the machine, but it gives me some good results. And then I'm going to go ahead and really just put it at the maximum that I can, which is 927. Okay. And now to save in the real world, I want to save my machine. So I'm going to flip that off. Drop the power. I'm going to stop this. Let me see if I can actually stop it that way. Does the same thing. Okay. Here's our data. Tell me when you are done collecting your data.
I got it.
Okay, Braden.
I'm good.
All right, so let's go ahead and export this. We'll call it lab, I think this is lab 6. We'll call it Wednesday. We'll export it. Then in Excel, I'm going to go ahead and open a file. Let me bring this over here so you can see. Browse, that's under the downloads directory. And I have to do it as a TXT file, so that's why it's not showing up. So I'm going to do all files. Here's the Wednesday. Open it up, and it's going to be a it's comma values. So I hit finish, and here's my data. Now, you want to go ahead and save this file, because if you try to start creating curves in a TXT, it's going to give you a lot of heartburn. So make sure you hit save as an XLS or workbook file. Otherwise, you won't be able to create curves. Okay. All right. So the first thing we're going to do is, so on part 11, it says, obtain a graph of motor line current as a function of the field current. So motor line current, and just for giggles, I recommend this. If you move this over to the left of this, what's going to end up happening is this is your independent variable, your DC current. So this is my IF. This is my phase voltage, my line current. This is P total and Q total. This value here, if I set it up, it's going to make it easier to develop curves. It just assumes that the first value that you use is the correct one. So my first one I'm going to do is going to go field current versus armature current. So I select those two by holding down the control button. I'm going to insert a chart. This is an XY scatter. And here, whoops, is that current. Okay. And then you can go ahead and change the title. So this is field current versus armature current. And we can add our horizontal axis, which is going to be field current. And then our vertical axis, this is our armature current. Now, the question is, what field current is the value that minimizes the armature current? So essentially, where is this the minimum?
0.7 or 700 milliamps.
Yeah, right around 700 milliamps. Exactly. So what that tells me is this is the minimum amount of current that comes out of the machine or goes into the machine. But why does it start to go back up? Well, this is the case when I'm running very little field current. The machine is called underexcited. It needs support from the grid to go ahead and help set up the magnetic fields inside the machine. So in the underexcited case, its magnitude of current is higher because it's pulling in actual magnetic energy or magnetic current from the supply. As it gets more and more excited, it's still underexcited, but it's less underexcited until the point where it's essentially no longer underexcited and it starts to transition to overexcited is when my current equals essentially the minimum it's going to have. It still needs to draw current because remember, the power output of this machine is still between 126 and 92. So the power can't be zero, it's still outputting power. But if you look at this reactive power, right at about 700 milliamps is when it gets to its lowest value, minus 3.43. So at this point, the positive Q indicative over here means it's absorbing, it's taking power in until it gets to this value when it starts to export it. That's what the negative number means, because we talked about the direction of power. As a motor, P is in, and if it's positive Q, then Q is in, but if it's negative, Q is out. So at this point, it transitions from an underexcited machine to an overexcited machine. And that's the biggest advantage to these synchronous machines, is that they're able to provide reactive power support by adjusting their excitation system to either act overexcited or underexcited. So that sort of shows you that you can vary this value of field current, and the speed never changed. It always stayed at 1800 RPM. We didn't actually record it, but had you looked over here, this always would have stayed at 1800 RPM. Okay, so the answer for number 10 is around 700 milliamps. All right. Questions on that? Because that's exactly what we would expect it to do.
I think I got it.
All right, so let you help me out, do number 12. So for number 12, we want to attain a graph of motor active power and reactive power as a function of current. So let's put this on the same chart or the same plot. How would you go ahead and create a curve? Anybody want to volunteer to do that?
Just add a data series.
How do you do it here? I certainly can. The problem is this y-axis here is field current, or armature current, I should say. And it just goes from 0 to 1.2. The problem with that is that these values vary from 400 down to minus. So if I try to put this on this curve, this 1 point whatever down to 0.2 is going to get buried. So my suggestion would be to start and develop another curve. So I select those data points, I insert another XY plot. I'm going to put this over here. This is going to be field current versus P and Q. And now I'm going to get a little bit cute. And the blue line here you can see is the power. So when I select this data, I'm going to format this data series. Maybe I have to select data, sorry about that. So I'm going to edit series 1 and I'm going to call that P total. And this one is going to be Q total. So now my series look better. And then I'm going to go ahead and add my titles. So my horizontal is field current. Oops. And my vertical axis is going to be power. Okay. So at 700 milliamps, somewhere between here and here, what happens to that value of Q?
Does it become negative?
Yeah, it transitions from positive to negative or right around there. So when the value of Q is negative, is the same value that happens here. So the answer for number 13 is, what value does it go? It's at that same value that it minimizes that current. And that's because there's no Q, there's only P. So if you did the power triangle, your P and your S value would be the same. And since your current or your S is equal to the square root of 3 VI conjugate, if S is purely equal to P, there's no reactive power. That's going to be the minimum value that you would see. So notice that the power, as we vary the excitation, it changed a little bit at first, but it's pretty well constant line, especially when you compare it to what's happening with Q that goes from 400 down to minus 100 or so. So you can see this has a huge change, where this one has very little change. And that's, again, that's what happens in industry. As you're varying the excitation, you don't have a lot of change in the active power output. So the only way you would change the power is if you change the amount of load or torque on the machine. So if I put more torque onto the machine, then I would draw more current, and you would see this power going here. But this characteristic here, if you remember from class the other day, let's bring that up. Where is it? Generator curve. Oops, not this one. Do you remember when we were looking in class the other day when we started looking at characteristics? Well, inside here, when we were looking towards the end, we looked at those things called V curves, right? And isn't that pretty much the exact same case? This is field current right here. This is armature current. And you'll see, let me zoom in a little bit, that for a constant power output, because these curves are based on active power, 25%, 50%, 75%, and 100% of rated active power, 25, 50, 75, 100. So you can see as I go from an underexcited case, my armature current drops until it reaches unity power factor, and then it starts to increase again. So what you did in this lab is you built a V curve. So let's change the title to V curve, or add that to the title. So the last question asks you, can you conclude the motor line current is minimum when the reactive power is 0? The answer is yes. That's it for the lab. You do not need to do question 1 because you don't have the data. It didn't record properly. So you do not need to answer question 1. So that's all I had for lab. So I'll stick around and answer any questions you have, but I will stop the recording and answer questions.